Hey folks! Well, we've spent a long time getting to this point, but we're finally at the spot where we can start talking about having the compiler actually generate some code, generate some output for this. So first off, I want to talk about some generalities, and then we'll start getting into more and more detail over the next few sessions and see how we go. Alright, so again, as you know, there's a huge range of possible ways that we can produce output code that matches what the original source program was supposed to do. And especially if we're talking about assembly language as the target language, there's a huge number of different combinations of assembly language instructions you can use to accomplish any given task. And so the trade-offs that we're considering are how fast is that code going to run, how much memory is it going to use, how many registers does it require, how much energy does it consume when it executes. There's all sorts of different trade-offs that you can consider. So we're going to refer to code shape as being just a kind of general collection of decisions that we make from the kind of intermediate representation through the actual generation of the code that influences the code that we actually output. Right? The decisions that we make that impact how and what we actually wind up producing. And again, there's a huge range of decisions that are going to impact this. And a lot of the things that we talked about in that kind of intermediate or internal representation side of things fit into that scheme because, depending on how we do things in that intermediate representation, it has a huge impact on how easily or how effectively we can produce different forms of target code, right? What we wind up generating in the end. Things like the naming decisions that we made or the kind of memory model decisions that we were using as the basis for things. So these are all things that are going to influence the code that we start spewing out. So coming back and revisiting that storage idea. We talked about the idea of sort of a memory-focused model where we try and keep data in memory as much as possible. When we actually need to perform an operation on it, we move it into a register, do the operation, and then put it back. And then the other approach, the kind of register-driven approach, where we say, well, instead of moving it back and forth all the time, why don't we just assume that we're going to move everything into registers and keep them there as much as possible? When we absolutely need to, we'll move them back to memory. And, before you jump to another, before the scope ends or before you jump to another function or something like that, it's entirely possible you're going to have to put things back or if you pass by reference, you're going to have to make sure it's back in memory so that the function's got access to it. And there are times when we're going to be when we still have to move things back and forth. But as much as possible, we'll try and keep things in the registers. Then, in terms of things that are in memory, because stuff still has to be in memory, it's just for putting it in registers so that we can work with it. We still have to decide where things wind up in memory. So what goes into the kind of static or global space? What winds up on the stack? What winds up in the heap? How is it going to be laid out in each of those different areas? And we're going to have to need to make sure that our compiler, when it spews out code that follows the kind of processor and OS rules for memory handling. So usually the operating system is going to give you, the program, if you like, a chunk of logical memory space and say, here, this is your memory. And the operating system is making sure that that's all you have access to, and it's going to map that onto real physical memory someplace. And so when the compiler's looking at memory for a program, it's just thinking of it as this big one logical block, and that's my memory, and I don't really care how it gets mapped into real physical stuff somewhere down the road. Now, in terms of that kind of layout of logical memory, one pretty common approach is to say, well, I'm going to have all of the actual assembly language code that has to be in there somewhere, right? The instructions for the individual functions and et cetera, et cetera, et cetera. I'm going to have some space for global variables. And if there are things like static local variables in C, for instance, where you've got a variable value that's shared across calls to a specific function, I've got to have that in some kind of shared space as well. If we're using a runtime stack, then we've got to have space for the stack. If we've got dynamic memory allocation, then we've got space for a heap someplace. And again, a pretty typical idea is to have the executable code and the sort of static global space kind of pushed towards one end of our free memory. And then we'll have the heap and the stack in the chunk that's left over at opposite ends and growing towards one another, so that as long as there's free space in between them, the stack can keep growing and the heap can keep growing, and so they can grow and free and grow and free and grow and free. And you're making the best use you can of that space, rather than saying, okay, well, I'm going to give this half to the stack and this half to the heap, and you might find out the stack needs more and the heap doesn't need as much. So this is a decent balance between the two. Now, you've got the rules for data scope and data lifetime, variable scope, variable lifetime in the source language. And you've got the rules in the target language. And the compiler has to make sure it produces code that behaves consistently with those sets of rules, right? So that it behaves the way the source language, the runtime behavior is the way the source language says it should be, and the actual output code is valid in the target language. But beyond that, the compiler's got a fair amount of freedom as to what it does kind of on the side. If the compiler realizes that there's some temporary value that it computes that it winds up using a whole bunch of times, it can put that, somewhere in the global space, the static space, and say, I'm going to use this later, so I'm going to put that over there and use it whenever I want. Or it might wind up putting space in the heap or putting extra things on the stack, kind of administrative housekeeping information that's going to help it or is going to permit optimizations later down the road. So the compiler does have a kind of a lot of things that it can do that neither the source language nor the target language are ever really even aware of, and it's not relevant to them. It's just the compiler finding an efficient way to make things work. Right? The compiler can also do things like say, okay, well, you said you wanted variables A, B, and C in this particular function, so I'll put variables A, B, and C in that function, but the compiler might be free to rearrange the way they're in. It might not store it as variable A, then variable B, then variable C. Maybe it's C, then B, then A, or maybe it's C, then A, then B, etc., etc., etc. So the compiler can do some rearranging of things. And that's something else that we want to be aware of and look at when that's useful, and we also want to be aware of what the implications of that are. Right? So the compiler might try and rearrange things so that things that are used together wind up on the same page in memory, so that you get a good cache hit ratio. When you bring one in, you're going to bring the other in, and so you're going to have them both there. So there are all sorts of little things that we'll take a look at here. We've got, we'll get into this. So again, on the cache hit idea, right? If we think of the idea that our operating system has got our memory divided up into pages, and it only keeps some of them actually on hand at any given time, and so it might have a cache for things that it's using a lot, and so it's got these pages that it's used recently or used frequently sitting in the high-speed cache so it can get at them really quickly, but again, only a limited number of them. The compiler might try and do things to try and ensure that data values that get used close to one another come into the cache at the same time. Again, try and make sure that things are on the same memory page, for instance. Now, this gets a little bit tricky if things like your activation records start getting large. So if you've got a function with a whole bunch of local variables in it and some of them are big, then it can be tricky to try and ensure that things that are used together are on the same page, right? If your activation record spans a lot of different pages, then you can't really guarantee it, and so there's all sorts of different sort of heuristics that can be applied to try and improve the cache hit ratio, but this is something that you might focus on as a compiler writer. Then again, you've got the idea of trying to make sure that we're keeping memory as compact as possible. So we have to stick with whatever rules the operating system and the hardware has for memory alignment. So if they say that doubles have to begin on an address that's divisible by 8, floats have to begin on an address that's divisible by 4, shorts have to begin on an address that's divisible by 2, chars can go anywhere. So there's all sorts of different memory alignment rules that we have to adhere to. The programmer doesn't necessarily think or care about what those rules are, and so when they go through and define a bunch of variables in a function, they're going to list them in the order that makes sense from the way they're thinking about it as they're writing the function. So they might declare, a character variable, then an integer, then a long, then a float, then a char, then a double, then a char. The order isn't necessarily going to reflect the best way to organize them in memory. So if you've got these memory alignment rules, and let's say that the local variable space for the function begins on an address that's divisible by 8, for instance, whatever the most general address is, then if we've got something like a char int that the programmer has specified, if we just lay them out in memory the way the programmer specified, then yeah, the first character lands on an address that's divisible by 8, even though it doesn't really need it. But then we're on, an address that's divisible by 8 plus 1. So we've got an odd address that our integer variable's trying to sit on. So we can't put it there. So we wind up putting, we move forward until the next available boundary that fits for it. So we wind up with 3 bytes of wasted space, and then, padding. And then we put the x there. Oh, and then there's another char right after that, and that can go anywhere, so that's fine. But then again, we're on an odd address after that, and so we wind up with another 3 spaces of padding before we can stick the z in. And so you wind up potentially with all these little chunks of padding in between the variables to try and get the memory alignment right. So one of the things that a compiler might do is say, well, you shouldn't really care what order those variables are actually in memory. You just want to make sure that you've got storage for your 4 variables. So what I'm going to do is put the 2 ints first, right? So if that first one starts on an address that's divisible by 8, then 4 bytes later it's going to be an address divisible by 4, and then 4 bytes after, etc., etc. So the alignment works out well. So we put the 2 ints first, and then the 2 chars. And so that way we can guarantee that we've got no padding in there, and we've still got all the variables in. So we can make a better use of space, and I believe that this slide is saying pretty much exactly what I just babbled through. So the idea is the compiler can rearrange them from whatever the most restrictive data type is in terms of memory alignment to the least restrictive. So again, start off with things like pointers and doubles and longs, and then go to ints and floats, and then go to shorts, and then go to bools and chars and things. So this way, even though they're not in the order the programmer wrote them in, they're all still in there and you don't have any wasted space. Now, if the programmer is trying to get tricky and say things like, well, I declared variable x right after variable w. If I look at the address for w, then 1 byte later I should be able to see the address for x, then the programmer is going to be hosed. But we can go through and do things like this. You just have to be aware of the implications. And the programmer has to be aware of the fact that this kind of thing can be happening, right? If you're writing a C program and you have your list of variables, then you have to be aware of the fact that the compiler might be putting some padding in between them, or it might be going through and rearranging them. Actually, you'll see some programmers take advantage of knowing the padding rules and saying, well, I know that right after this char W or whatever it is, there's going to be 3 bytes of padding that aren't being used, 3 bytes of just wasted space. I'm going to use those 3 bytes of space for something. So you can get all sorts of weird and wonderful things happening, but not particularly recommended from a software engineering perspective, but again, something to be aware of. Let's see, and you can do similar sorts of things when you think about the layout of structs, right? If the programmer has a whole bunch of struct fields in there, then maybe the compiler is going to go through and say, you know what? Your struct is going to be more compact if I rearrange the fields in this order. But again, if the programmer is thinking of things as, oh, well, this field's going to start so many bytes after the start of the struct, that's not necessarily going to be the case. You have to make sure you understand what the padding rules are and what the ordering rules are going to be. Same sort of thing for parameters in a function call, right? You have to think about what order the parameters are going to be in. Quite often you'll find that with parameter lists in particular, the compiler might go through and say, you know what, I'm just going to, so that I've got if I'm pushing my parameters on a stack someplace, then maybe I'm just going to assume they all take whatever the default most restrictive ordering is, and we push them all on boundaries divided by 8. Or divisible by 8, something along those lines. However, we will come back and address that stuff more as we get into parameter passing later. Now, we've got the sort of these memory issues to deal with, and again, as I said, we'll we need to come up with some sort of a decision on what kind of a register-based approach we're going to use. And what I'm going to do, and we'll talk about this more in bits and pieces as we get through the rest of the term, but I'm going to assume that we're using kind of a register-focused model where every value gets its own virtual register, and we try and keep it there as much as possible. So, if you've got a variable x, you copy it to a register, work with the register as much as possible, and when you need to, you put it back in the memory space for x. Now, that does assume that somewhere later on, we've got a good register allocation algorithm that can actually map these kind of virtual logical registers to the real physical ones. But again, it keeps our intermediate representations simpler, and it still gives us the good possibilities for optimization as we go through this process. Hopefully we'll have time towards the end of the course to get into some of the register allocation schemes. Now, one of the other things that I wanted to get into on that note is if we're putting things in registers, if we're putting values in registers so that we work with them there, then we have to be sure that when the code refers to something by name, refers to variable x, for instance, that we're actually using the right register. And if we're putting values in registers, then we want to make sure that we know that we're getting the right values in terms of what the program is trying to refer to. One of the places, well, I guess if we're dealing with straight variable names, usually it's unambiguous. If folks are referring to variable x, it's variable x. It's pretty clear. But as soon as we start referring to, as soon as we start using pointers, for instance, and saying, okay, well, I want to refer to the value that x is pointing at, then it's much trickier to tell when we're talking about the same value or not. We'll come up with a couple of examples in this in just a second. But working with things like arrays, where we're using variables as the indices into the array, and where we're dealing with indirect references through pointers, these are all going to be cases where we start seeing ambiguity creep in. So here's a couple of examples. Suppose I've got two references to values in an array. So at one point in the code, I refer to the value that's in position mn, and at another point I refer to the value that's in position ij. At compile time, we can't really tell if those are referring to the same location or not. So we can't really tell if we're storing those things in registers, if we're throwing array mn into a register to work on it, and we're throwing array ij into a register to work on it, we can't really tell if those two registers are supposed to be referring to the same location or not. The same idea if I've got a value that x points at. If I throw that in a register, and I've got a value that y points at, and I throw that in a register, it's hard to know if the values that are in those two registers are actually supposed to be the same thing or not. If they're really supposed to be referring to the same memory location, if you like. And we can go through and actually do comparisons and say, okay, well, if x is less, or if x is equal to y, then they're referring to the same place. Or if m and I are equal and n and j are equal, then they're referring to the same array element. But that relies on the compiler sticking in the extra code to make those comparisons, to figure things out at runtime as to whether or not we've got two similar values. So here's an example. Let's take a little chunk of code, and this is one of our pointer-based ideas. So we'll say, in the location that x points to, we're going to store I plus j. And then in the location that y points to, we're going to store a 1. And then in z, we're going to store whatever x points at plus whatever y points at. Now, if x and y are different, if they're pointing at different places, then z is getting I plus j plus 1. But if x and y are pointing at the same place, then we're putting I plus j in that place, and then we're overwriting it with a 1. And so when we do that last operation, we're saying, well, it's getting, since they're both pointing at the same place, it's saying we're getting 1 plus 1. So this is either going to wind up with a 2 in it, or with an I plus j plus 1. And this is one of those examples where if we're generating code and we've got these two values in registers, it's hard to know when we assign a value through y if we should be updating x's value. right? If we should be overwriting x's value. And this is where some of the ambiguities come in, right? Some of the ambiguous references come in. So again, the compiler could go through and insert code that will resolve those ambiguities at runtime, so test if x and y are the same, and if we make an assignment to one, then we've got to make an assignment to the other, or use the same, copy the values into yet another register and use that one to update both of them. Or we could go through and simply say, okay, well, you know what? If there's ambiguous references, then I'm not going to try and figure out things. I'm just going to put x and y back into their proper locations. I'm going to essentially put them back in memory rather than put my x value back in x and put my y value back in y, rather than continuing to work through the register for them. So these are cases where it's kind of like our pass by reference ideas, where, okay, well, if I'm going to do something that's potentially going to change the memory location, I've got to make sure that I've got the correct address in the correct place to do that. So these are all things that we'll want to try and address as we're generating the actual code over the course of the next few weeks. So what we'll do next is take a look at the actual code generation process in general. So if we start from some kind of a tree representation of our program, how do we get from that to actual output code? So we'll take a look at a little tree walking algorithm. All right, that's a good place to leave it for now.